Hi everyone. Today I'm going to present this work, CaliQEC, In-situ Qubit Calibration for surface code quantum error correction. So this will be the structure of the presentation. I'll first introduce some background on QEC, error drift, and calibration. And based on that, I will describe the problem that we want to address, introducing the challenges and opportunities, which finally leads to our solution. And finally, I will give some evaluation highlights. So first, let me introduce QEC using one sentence. It's about using redundant physical qubits to form logical qubits to gain resilience against errors. And recently, this field has witnessed an amazing progress. So last year, we have multiple research groups demonstrating the surface code, one of the leading QEC solutions in various hardware platforms, including the Google superconducting device and QRS neutral atom device, and a few others. So the amazing thing is that they demonstrate the threshold theorem, which claims that the logical array will be exponentially suppressed if you increase the system size, given that the physical array is below the threshold. So the key takeaway here is that you really need to maintain a low physical array in order for QEC to perform well. However, in Google's paper, they reported that there are actually some variations in the real-world hardware conditions. So factors such as cosmic rays and manufacturing defects or error drifts can largely compromise the performance of QEC during the runtime. So our group had made a few attempts trying to use the software solution to tackle these hardware issues. So last year we had publications of the former, and our target will be our target was the dynamic defects, and the work I'm going to introduce today, we target for the error drifts. So what is error drift? It's just a fancy name for physical error will increase in time. So this is a common behavior in lots of in superconducting device. So this is our target. So we collected data from the real machine from IBM, and it shows that over 90% of the qubits will drift over the threshold in 24 hours. So this is a distribution, and even if the physical error is below the threshold, a higher physical array just means that you need to. It just means a worse logical array, and you need to encode with a larger code distance to maintain the original level of logical array. So how to address this? The standard approach is called calibration, which Yuchen Zhou had discussed yesterday in depth. So it will first characterize the system and gather information from the current like qubits properties, and then it will fine-tune the gate parameters to their optimal values, and then recover the physical array to the original level. So this is how it works. So as you can see, this is the data we collected from IBM machine. You can see that the physical array actually drifts over time, and after this calibration, which is this blue region, takes about 1 hour, the physical error rate actually drops down to the previous level and starts to drift again. So here are a few key takeaways. The first is that I want to emphasize that the calibration during this characterization stage, it will perform some specific operations on the qubits trying to extracting some informations. So that will destroy the quantum states and disrupt the ongoing computation. So the standard approach is that during calibration, we just don't perform any like quantum computation. And the second thing is, well, calibration has to be performed periodically, like every couple of hours, because you can see the physical array drifts consistently. And the third thing is that a lot of resource estimation paper pointed out that for the future large-scale quantum application, they typically span from hours to days. So this cannot be possibly done if we have to just stop the whole system for calibration every couple of hours. So here the challenge is that the need for calibration inherently conflicts with the long-time fault-tolerant quantum computing. So now we have identified the problem that it's a conflict between the calibration and the computation. So there are a few natural naive solutions. So the first one is just to increase the codistance, but as you can imagine, although this can temporarily reduce the logical error rate due to larger distance, the error drift will eventually make the logical error rate exceed the target level. So this doesn't help essentially. And the second natural solution is more practical. We call it logical swap for calibration. So the key idea is that whenever you have a qubit that you want to calibrate on some logical patch, then you first transfer the logical state to somewhere else. And then you perform the calibration on that region. And after the calibration is done, you transfer the logical state back and potentially work on some other qubits need to be calibrated in that region. So the good thing about this approach is that you don't need to stop the computation. You can perform the quantum computation along with the calibration. However, this is definitely not, this is far from an optimal solution due to the several limitations that I will introduce next. So, first, this logical transfer is not as simple as we might have thought, because it actually involves some complex physical operations. You need to, especially for the superconducting device, you need to initialize the qubits and perform the stabilizer measurements, and then measure some qubits to deform the boundary. And moreover, this will this will require extra space to accommodate the logical state that being transferred. And the second thing is the transfer and calibration are performed separately, so that introduce extra time overhead. And finally, this is a coarse-grained approach, meaning that whenever there's a qubit need to be calibrated, you have to move the whole logical qubit to somewhere else, even if the qubits even if the rest of the qubits don't need calibration, we still need to do that. So the frequency of the calibration or the transfer is determined by the shortest period of the qubit within the code patch, and that will lead to a high frequency of like transfer and the calibration, meaning more errors and time overhead. So we want to address these limitations and ask this question: so can we actually efficiently integrate runtime calibration with ongoing computation while maintaining the protection level of service code? So of course, then the answer is yes, and I will present our solution. So the key idea is that we will use the code deformation technique from the surface code to isolate the qubits that need to be calibrated. And during the calibration, this will not affect the rest of the qubits in the patch. And the important thing is that this qubit isolation process is information preserving. So it only changes how you encode the information, but doesn't change the encoded quantum information. So it doesn't interrupt with the interrupt the ongoing computation. Yes, but since we reduce the qubit redundancy, so the QEC capability might be compromised, and that's why we enlarge the code patch to restore the code distance and to maintain the logical error at the target level. And after calibration, this qubit can be reintegrated into the system, and we can potentially work on other qubits that could be calibrated. So yeah, so let's compare these two solutions. So compared to the baseline, our solution can achieve the in-situ calibration without moving the logical states around, and it can achieve the concurrent calibration along with the program execution. And finally, it's fine-grained, meaning when you calibrate one qubit, it doesn't affect the other qubits in the patch that currently don't need to be calibrated. So it's not hard to imagine that this will give a better performance in the evaluation part. But before that, let me just give a little bit more details. So this framework consists of like 3 stages. So in the first stage, preparation time, we characterize the device, meaning that for each gate that will potentially be calibrated during the long time computation, we generate a calibration profile for it, specifying the calibration duration and the drift rate, which relates to the frequency of the calibration, and the neighboring qubits that will be affected by the calibration of gate G. So these neighboring qubits will also be isolated during calibration, along with the qubits involved in the gate G. So this can ensure that the calibration will not affect the rest of the system. And based on this calibration profile, you can generate the calibration workloads specifying by the duration, frequency, and crosstalk constraints, which specifying that, well, which calibration workloads cannot be performed together. So next, during compilation time, this is still before the runtime. So we group these calibration workloads according to their frequencies, and within each group, do this scheduling, respecting the crosstalk constraints while minimizing the total calibration duration. And after that, during the runtime, based on this calibration workload scheduling, combined with the code deformation instructions that can isolate the qubits affected by the calibration without changing the logical information. So we perform this deformation first, and then calibrate the qubits or the gates, and obtain the optimal parameters and restore the low physical rate. And importantly, this is concurrent with the ongoing computation. So yeah, let me present some evaluation results. So in terms of the overall performance, we perform the end-to-end evaluation on the standard fault-tolerant benchmarks. If you look at this column, you can see that if there's no calibration, the retry risk or the failure probability is around 100%. So that means calibration is indispensable. So this is straightforward, but in this case, the number of physical qubits and the number of execution time is optimal. So that serves as a good reference for evaluating the time and space overhead. And when comparing our framework with the baseline, we can see that there is a significant reduction in the qubit count, the execution time, and the retry risk. So this is because we don't need to set aside an extra space to accommodate the logical state being transferred, and we reduce the number of logical operations. So due to the transfer, right? So we reduce the execution time and the retry risk. We introduce less error. And comparing to the no calibration case, we maintain the optimal execution time because we don't introduce like extra logical operations, and we can also suppress the retry risk to the target level, like around 1% and like 0.1%. But this only introduces a mild qubit overhead around like 24%, because it only involves enlarging the hash by a little bit to restore the co-distance. So during the computation, this is what's happening. The logical error rate will drift due to the error drift of the physical error rate, and when it almost reach the the target level, we will perform this qubit isolation and and code enlargement to keep the logical error rate under the target level. And if you don't perform this enlargement, there will be a spike due to the distance loss after the qubit isolation. And if there is no calibration, then the logical error just keeps going up. And here are a few ablation studies just showing the effectiveness of our calibration grouping and calibration scheduling, but I think I will skip that. And finally, I will mention some my personal perspectives on this project after everything is done. So the key insight from this project from my perspective is that hardware issues can actually be mitigated by the software solutions, and sometimes this can be more effective and practical than the hardware technology alone. And the second thing is that I really found like gauge fixing a fundamental technique in QEC, and it has lots of potential from the first subsystem codes when it was proposed to later lattice surgery and logical operations for quadratic cycles, code switching, and in this work used to mitigate hardware issues. So I believe there are also lots of other QEC techniques that have already been developed that we can use to tackle the emerging problems like in this area. So that would be, and I'm happy to take any questions.